All right, number one, the recordings were done. You know, last night, I guess when I was checking, it wasn't done, but this is a new link, so they're done. I'm downloading them right now. And so you can access those on Canvas right now, and then I'll upload this to YouTube, post a link on Piazza. Here's the background for Aaron Brockovich. You know, it's the hexavalent chromium, also written as chromium. This is Roman numeral, chromium 6. It's in the +6 oxidation state, so chromium 6 or chromium 6. Hexavalent chromium is going to occur in like chromates and dichromates. You know, chromates and dichromates are going to have hexavalent chromium in there. It's not a free ion. You know, it's going to be complex with other stuff. So this is what hexavalent chromium is used in other things like certain stains for concretes and other things, but it's a carcinogen. Here, chromate is typical for chromium 6, dichromate as well. You know, chromate and dichromate have this same. There's trivalent chromium, which is chromium 3, which is common. Divalent chromium would be chromium 2. But apparently the town of Hinckley, don't drink the water in Hinckley because the water supply has been contaminated with chromium 6. Actually, this was settled, you know, it's a PG&E site. And so it's a California utility ended up paying $333 million, which is the largest settlement ever paid in a direct action US lawsuit. The law firm won 133.6 of that. And Brockovich got $2 million out of that. But unfortunately, a lot of people ended up getting cancer, 196 cases of cancer. You know, before that, you know, it was just random. But after the water supply was contaminated, then it became a cancer hotspot. 2016, the levels have gone way down. Now the chromium 6 levels in Hinckley are only 1.19 parts per billion, with a peak of 3.09 parts per billion. And so I guess they cleaned it up, but still there's some, you know, hexavalent. I don't know what it is in Torrance, but they do analyze for hexavalent chromium in Torrance in the water supply there. Okay. So let's continue on. Here. What we're doing is we're just trying to, you know, look at the observations and see if we see some patterns. And we already saw some patterns, fluorine, chlorine, bromine, iodine. Then we see patterns with the oxyanides, you know, peroxides are good, you know, certain elements are good, the ozone, oxygen, good. Fluorine, of course, is excellent. And then other species which have, you know, are electron poor, like dichromate, you know, who's chromium 6, permanganate, which is manganese 7. Because manganese 4 is decent too. You know, manganese 7 is better, but manganese 4 is pretty good. This is IO3 minus. What's IO3 minus called? IO3 minus is iodate, good. And that per iodate is going to be better, you know, but iodate's pretty decent. Chlorate should be better as well than iodate. Chlorate's not on here. There's certain things that aren't on here because they try to keep this list compact so it fits on a page. So this is why it's a surprise, you know. This is a heavily edited list. So rather than copper 1, they should use copper 2. Copper 2 is a different ranking, you know, because it's more common. They should eliminate cerium 4, you know, cerium 4 is not that common. They should put something else in its place, like chlorate. Chlorate's a lot more common. Or perchlorate, you know. We'd like to know where perchlorate lines up here. It's up here, it's strong, you know. Iodate's decent. Iodine, this is -6 plus 5. Iodine's plus 5 in iodate. Nitrate's up there, you know. Nitrate's better than silver ion. You know, we saw that ammonium nitrate explosion. That was huge. Because the nitrate's a powerful, well, how powerful? It's not as powerful as these, but it's a pretty strong oxidizer. So we'll just say it's a strong, moderately strong oxidizer here. Now, if you take a moderately strong oxidizer, and react it with a powerful reducer, and then you're going to get an explosion, that kind of stuff. So it depends on what you're reacting with. Higher charge ions like tin 4, tin 4 is better than tin 2. Tin 4 wants electrons more than tin 2. Sulfate isn't that great, sulfate is, although sulfur is +6, so this is hexavalent sulfur, but it's not like chromium, there. So sulfate's down here. It's a little better than tin. Sulfur is a lot weaker than oxygen. Oxygen is a lot smaller. We talked about oxygen. Actually, oxygen is way up here. Sulfur is way down here. Sulfur is a lot bigger. So oxygen is a lot smaller. So oxygen is going to take electrons more bigger. But sulfur is still better than H+. H+ is mineral acid, or the acid. H+ is acid, I'm just saying. Then we have these cations here, like lead 2, all these. The weakest is lithium ion here. And so we can kind of get an idea. These are the oxidizing agents. And on the opposite end, we have the reducing agents. So this is the activity series upside down. The activity series begins with lithium. Lithium's at the top of the activity series. So we have to look at this upside down. Lithium being the strongest, then potassium, calcium. So we're going downhill like this, inverted. H2S is a decent reducer, here. So metals are good reducers. Hydrogen's a good reducer. H2S's. So we were talking about, you can burn H2S, it's a good reducer, but you aren't going to burn water. Water looks like it's at the bottom. Well, where is water, actually? You can burn H2S. This is the wrong water. This is water as the oxidizer. We need water as a reducer. Now, when we look for water as a reducer, here's a water, but it's combined with something else. We want water just alone. And so if we look at water just alone, here it is. But this is forming H2O2. We don't want that. We want water forming here, the oxygen. And so this is the water we'd use. And so water is pretty tough to burn, tough to oxidize compared to H2S. H2S is much easier. So H2S is a much better reducer than H2O. And sulfur is much bigger, so it's easier to take the electron off with that. Tin 2, this is sulfur dioxide. Sulfur dioxide, sulfur 4, going to sulfur 6 in sulfate. Copper metal, iodide, hydrogen peroxide we saw before, but this is a hydrogen peroxide losing the electron. Remember, oxygen can go from -2 to +6, and so it's -1 in hydrogen peroxide. So it could either lose or gain. In this case, it's losing to form oxygen. Over here, it's taking electrons to form water. And so hydrogen peroxide is what we call a species that's both an oxidizer on the left and a reducer on the right. So it can do either gain electrons or lose electrons. What happens to hydrogen peroxide depends on what you react it with. Certain things can go both ways. Iron 2. Iron 2 can go both ways. Iron 2 can lose electrons to form iron 3, or iron 2 can gain electrons to form iron metal. And so iron 2 occurs on both sides. Species that occur on both sides are both an oxidizer and reducer. And their role depends on what you react it with, So NO, nitrogen monoxide. Nitrogen monoxide can lose electrons. This is nitrogen in the +2. It can go nitrogen in the +5 in nitrate. Bromide can lose electrons to form bromine. Now this is weird. Iodine loses electrons. Iodine loses electrons to form iodate. And so iodine is 0, iodate is +5. Going backwards, we're going backwards here. Water can lose electrons. It's not the hydrogen in water that loses electrons. It's the oxygen in water. The hydrogens stay the same, +1. But when we look at the oxygen goes from -2 to 0. So the oxygen loses the electrons here. Manganese can lose electrons here, going to manganese 4. So we're going from manganese 2 to manganese 4. Chromium 3, this is trivalent chromium, can go to hexavalent chromium here, losing electrons. 2 of them, each of them losing 3. Go to chromium +6. Chloride can lose electrons. This is lead 2 sulfate. Lead 2 sulfate can go to lead 4 oxide in this particular reaction here. This is manganese 4 oxide. It can go to permanganate. So we've gone from manganese +4 to manganese +7. cerium-3 going to cerium-4, water going to hydrogen peroxide, but there's another water here. We should use this water going to oxygen. This is a stronger water. This is a weaker water here. This sulfate going to the disulfate here, but this disulfate's different than dichromate, you know, because of the peroxide link. This is oxygen going to ozone, losing electrons here. Oxygen and water, you know, we need that water because the water is going to be losing electrons in this. Nothing's happening with oxygen going to ozone. It's going from 0 to 0, fluoride. And so, you know, once in a while we'll, you know, well, of course we're not going to memorize this, but once in a while we'll take a look, you know, see if we see some patterns there that help us remember, you know, these types of things. You know, periodic table is also helpful in helping us remember these types of things. The most powerful reducers down here, except lithium, you know, is out of place a little bit, but lithium is down there. Most powerful oxidizers are up here. The noble gases are neither. Some of these species can act with both oxidizer and reducer. And so the chart method is, we're just going to use the chart here, this chart. Actually, this is the chart from Chem 1A. The chart from Chem 4 is a little shorter than this. Chem 1A also has a bigger chart. Let's actually look at the full Chem 1A chart here, just to give you a perspective on it. And also, let's try to understand redox chemistry a little bit more by looking at more species in the charts. And so I'm going to go to the Chem 1A book. Let's do that. The chart in Chem 1A is like 5 pages long. So let's take a look at that. Chem 1A, Chem 1B. Excuse me. Okay, here's fluorine. Fluorine's still the strongest, even in this more comprehensive chart in Chem 1A. But number 2 is not ozone. Number 2 is OF2, oxygen difluoride. Oxygen is +2 here, so oxygen's pretty unhappy at +2, and it's going to go to -2 here in water. Nothing's going to happen to fluorine. Fluorine goes from -1 to -1, so, and nothing happens to H. H goes from +1 to +1. So the only thing is the oxygen, you know, here is going to take electrons. To go from +2 to -2, it's going to need 4 electrons. 2 electrons to go from +2 to 0, and then another 2 electrons to go from 0 to -2 in water. There's ozone. Here's that disulfate thing. Ooh, this is really weird charge. What's weird about this? Somebody tell me what's weird about that. Well, one thing that's weird is I told you that silver is fixed charge. Silver is a fixed charge at, what's the charge on silver? +1. Here, this is a very unusual species. This is rare. This is why our table doesn't have it, but this would be very unusual. Silver with a +2 charge, making it extremely reactive, not very stable, not very happy. And so silver 2 ions are very reactive. And so this is why when we normally think of silver, we only think of 1 charge, and that's +1. And so sometimes we see these, but this would be rare. Cobalt 2 and cobalt 3 are very common, but cobalt 3 actually is very rare. Cobalt 3 is very rare because it's so reactive. You know, cobalt 3 really wants an electron to form cobalt 2. So cobalt 3 salts are extremely rare. Just like silver 2 is like finding a, what's really rare, finding a 4-leaf clover kind of thing, you know. It's not that common in a compound. Hydrogen peroxide is very common. They have cerium, here's permanganate, lead 4 oxide, manganese 3, gold. Gold wasn't on that other chart, so here's the placement of gold. Gold 3 is a pretty good oxidizer. Gold likes 1 and 3 as its charges. Here's permanganate again. So why do we have 2 permanganates? Well, one of these permanganates yields MnO2, the other permanganate yields Mn2+. So typically if we have 2 of these, we pick the stronger one, you know. But if in our chart, we only have this one down here that goes to manganese 2+, so that's the only one we'll use. Here's bromate. We had iodate, I think, in our chart. Lead 4, chlorate. Okay, so chlorate versus bromate. Oh, it looks like bromate's stronger. I wouldn't have predicted that. That's interesting. Well, this is why we need observations sometimes, observations to make sure, you know, whatever we predict has to agree with factual knowledge. Chlorine, dichromate, thallium 3+. You know, thallium's not one of those elements I asked you to memorize. Thallium 1 salts, you know, thallium's a 1,3, and so thallium 1 salts are highly poisonous. And historically, thallium salts have been used as poisons in the medieval times. MnO2, O2, iodate. Here's perchlorate. So finally, this perchlorate. Interesting. This is very interesting because perchlorate is weaker than iodate, but perchlorate's forming chlorate in this particular one. And so that explosion in the Nevada desert was not perchlorate going to chlorate, it was perchlorate going to something way lower. And so, you know, again, this is not always comprehensive and conditions can vary. So the chart method is not always perfect depending on the conditions. Nitrogen dioxide, bromine, NO2. Oh, this is a weird species, AuCl4 minus. This is what we call a complex. We'll talk about later. Here's nitric acid, nitrate, and H+. You'll notice a lot of these have H+. And the reason a lot of these have H+ is we need H+ to form water. So for example, here, 12 H's can form 6 waters. 2 H+ can form 1 water. 4 H+ can form 2 waters. 14 H+ can form 7 waters. And so we're getting rid of the oxygens, combining them with water to form water. I mean, combining it with hydrogen to form water. And so you can see this pattern. This is a pattern you see when you look at this for some time, you know. We can see other patterns. The thing is, in order to recognize patterns, you got to look at it over and over again, you know. Sometimes it's hard to see the patterns. When we look at this, it just looks like a jumble. It's like a jungle of data. How many pages is that? So we had a half a page. This is 1 page. Oh, I guess it isn't that long. 2 pages, 2.5 pages. I guess it's only 2.5 pages long. 1, 2, 2.5 pages. But when you look at this, it just looks like a confusion, you know, mass confusion, too much data, you know, and that's normally what happens. You get too much data, but what you got to do is you try to refine that data, and you try to look for patterns, simpler patterns, this kind of stuff to help you understand the data better. There's an interesting TED Talk. This was in the social sciences. The social science researcher said, you know, when she's doing, when she's looking at her raw data, you know, she throws all the papers on her floor, grabs a chair, and just sits and then just stares at the data. So this is the same kind of thing you could do with this. You just stare at it, or actually don't stare, you got to actively work through it, like we've been doing, to see patterns. And then you can see patterns. Once you see those patterns, you know, because this list, of course, is not comprehensive. Once you see patterns, then let's say you're given something not on the list. You know, when people are given something not on the list, one of the responses is, hey, that's not fair. You know, that's not fair. The book never talked about that. Well, nobody's going to care if the book never talked to it. They want the answer, you know. This is what I call that scrutiny, you know. And so if something's not on the list, you might be able to place it on there, just based on, you know, your understanding of the patterns that we see, you know. There are reasons why something doesn't occur on this list. One, there's not enough space. So something could be important, but not enough space. This is why I said, you know, why put cerium in there? There are more important things that could be placed on here that are more common. And so they try to pick the most common things. Yeah. That's one reason it's omitted. There's not enough room. Even though it might be important, there's just not enough room to put it on the list. There's 2.5 pages. Maybe that's half a page too much. Okay, or two, it's just not very reactive. So I would say that's for CO2. You know, CO2 is not very reactive. It's not that strong of an oxidizer. And so why bother putting it on this list? That's it. And so CO2 is not very reactive, so that's why it's probably not on this list. However, ethanol is not on this list either, but it is highly reactive. And so that's another reason why it just got omitted off the list, but it's important, you know. So there are two reasons why you might not see something on the list. It's unimportant, or it's important, they just didn't have enough room. That being the case, we want to know patterns so that we can try to place things, you know. You saw how the ethanol burnt in the reactor, you know, in the engine. And so that tells you ethanol is pretty powerful. I mean, does ethanol burn more violently than copper metal? Yeah. Yeah. Does ethanol burn more violently than aluminum metal, that powdered aluminum? I'd say yes. You know, and that helps you place things in here. Ethanol is a powerful reducer. So we could have placed it here, regardless if it occurred on this list or not. So, you know, these are the types, we want to know patterns, because, you know, the people who just do memorization alone, either know it or they don't know it, you know? Hey, I didn't memorize that, therefore I can't answer that question. But the people who know the patterns, you know, patterns of reactivity, learn a little bit more in depth, can place it, you know? Okay, ethanol's not on the list, but I know it's a powerful reducer, you know? And so which camp are you in, you know? Are you in the camp that, hey, that's not fair, that wasn't on the list, you know? Or can you think of it a little more deeply than that? You know, and then there are people who can't even get to the level because, you know, they try to cram this in one night, you know, everything in one night, the night before the big test. And they really aren't going to get much of anything out of this. This is just going to be a big jumble of numbers. All right, so this table is divided into two, you know, pH neutral and what we call acidic pHs, and then basic. And here's sulfide here. It's a pretty decent reducer. What else? In the basic end. Lithium is the strongest reducer, or neutral in acidic solutions. All right. So what we're going to do is, or we're going to just use the chart method. We could use the chart method for everything. You know, we don't have to use single replacement. And so what is the method? The method is inventory the major species, find the strongest OA, find the strongest RA, combine the half reactions, balance electrons, determine driving force. Okay, so let's do some here right now. Let's go back to copper with nitric acid. We know that this is going to fail using single replacement because nitric acid is an oxidizing acid, so it's going to fail. And I didn't memorize the pattern for this. And so I want to figure out what forms from copper and nitric acid. And what forms? What do we predict? All right, so the first step is to inventory. So what we're going to do is major species. So copper doesn't dissolve in water, so we're just left with copper metal. But nitric acid dissolves in water. Not only does it dissolve in water, it's a strong acid. So strong acids are strong electrolytes, so they dissociate into ions. And so I'm going to have H plus ions and nitrate ions. And then there's one more species that's not shown here, and that is from aqueous, water. Water is a major species that's present. And so these are the major species: copper, metal, H plus, nitrate, and water. Okay. Then we're going to use the chart. When we use the chart, we look for copper. Okay, and so I'm going to look for copper on the chart and see which side is it. You probably can already tell. Start off with fluorine. Let's work our way down. Here's copper ion. But I don't see copper metal. Copper ion and copper metal are two different things. Let's start at lithium and work our way up. Here's copper metal. So copper metal is on the lithium side. So what we do is we call it a reducing agent, Ra. Again, I shouldn't, this is screwed up because I'm using this one. Then we're going to go to H plus. H plus, I see it here. That's an oxidizing agent. Then we go to nitrate. Nitrate is here. I see that. I need nitrate and H plus. I need nitrate and H plus together. Why do I need the H plus? Because the H plus is important. I have 4 H pluses to form 2 waters. If I don't have the H plus there, then I form oxide, which isn't as stable as water. And so H plus alone is an oxidizing agent, and nitrate in combination with H plus is an oxidizing agent. Then I have water next. Water actually occurs on both sides of the chart. So water can be an oxidizer. It's not the greatest oxidizer. When we place it, it's between zinc and aluminum. And so we have water as an oxidizer, but water occurs on both sides. And up here we have water as a reducer. And so it can go either way. Water can go either way. It can be an oxidizer or a reducer. And so I write OA/RA. Now I'm going to pick the strongest oxidizing agent. So which one of these oxidizers is closest to fluorine? So let's go back, take a look. So I start off at fluorine and I look for H plus, OA, nitrate with H plus, OA, and water, OA. So I go down the list. The first one I hit is nitrate and H plus. The next one I hit is H plus, and the last one will be water. And so the strongest OA here is going to be H plus and nitrate. H plus and nitrate. Then I want to find the strongest RA. So I have 2 RAs, copper metal versus water. So let's start up with lithium, work our way up. The first one I hit is water, but that's water with sulfur dioxide, so I can't use that. I don't have any sulfur dioxide. Then I hit copper here. Where's water alone? Water alone's way up here. So copper is the strongest RA on this chart. And so the reactions, if there's a reaction, it should be between copper and nitrate and H plus. Here. And what I'm going to do is I'm just going to copy down what are called the half reactions off the chart. So when I look at nitrate, it's nitrate plus 4H plus, plus 3 electrons, yields NO gas plus 2 waters. And so that's what's happening with nitrate and H plus. Now what's happening with copper? when I copy copper down, I have to reverse it. And so copper occurs on the right side. So I flip the equation over to go from copper to copper 2 plus 2 electrons. And so that would be the other reactant. So I'm reacting copper metal with nitrate and H plus. Let's take a look at the chart from your book to really position copper, and we'll see that. Here. Let me, I'm just going to clear these drawings. Just redo it. Now, the chart in your book is in chapter 19. But I'm not talking about chapter 19 because chapter 19 talks mainly about batteries. I just want to talk about the reactions, not batteries yet. So batteries, strength, here. Oxidizing agents, reducing agents. So fluorine's at the top. Fluorine's the strongest oxidizer. Here they have gold 1, gold 3, chlorine, oxygen, bromine. Here's nitrate and H plus. This is called nitric acid. So this is what I wrote on the page. Nitrate plus 4H plus 3 electrons yields NO plus 2H2O. Now copper, we have to go backwards because here, this is copper metal on the right, this is copper ion. So what I need to do is I need to reverse this. So I picked the stronger of the two. Which one's stronger? Well, copper going to copper 2 is stronger than copper going to copper 1, if I have a choice, because the strongest is going to be lithium. So which one's closest to lithium on the right side is going to be stronger. So I'm going to pick this copper here. Copper goes to copper 2 plus 2 electrons. So I'll write those two down. And so these are the, what we call the half reactions. And so this one here. And then what I have to do is I have to reverse this one. Oops, not this one. I have to reverse this one here. Because I have copper metal, I don't have copper ion. And so I'll write them over here. Nitrate plus 4H plus 3 electrons yields NO gas plus 2H2O liquids. These are aqueous. Electrons are transferred directly. And so where do those electrons come from? Those electrons are going to come from copper. And so we have copper metal, and that's going to go to copper 2 plus 2 electrons. So this is going to produce 2 electrons. So I'm writing this one backwards because I have copper metal, I don't have copper 2. The copper metal can go to copper 2 plus 2 electrons. Well, nitrate wants 3 electrons, copper gives up 2 electrons, so there's a mismatch in electrons. Do you see the mismatch? 3 electrons we need here, 2 electrons are produced. And so the way we're going to fix that mismatch is by changing the numbers. And so what we want to do is I'm going to multiply the top equation by, in fact, I'm just going to double the top equation. And so this top equation, I'm going to multiply by 2 times. 2 times 3 is 6. And the bottom equation, I'm going to multiply by 3 times. 3 times 2 is 6. So we get 6 electrons consumed and 6 electrons produced. And then we add it up. And so when I add it up, I'm going to have 2 nitrates altogether, plus 8H plus 6 electrons. And then what I'm going to do is, those are all the reactants from the top equation. I'm going to combine it with the reactant on the bottom equation, which is 3 coppers plus 3 Cu solid. So I add everything up on the left. And then I'm going to add everything up on the right. So it's 2 NOs. This is going to produce 2 NOs. NO is a gas. Plus 4 H2O. That's the top equation. And then I'll add it to the products of the bottom equation. Plus 3 Cu2 plus 3 times 2 is 6 electrons. The electrons must cancel. So 6 electrons are consumed, 6 electrons are produced. And so electrons must cancel. So we got to multiply it by some factor that allows us to cancel out the electron. I'm going to see if there are any spectators here to cancel. There aren't any here to cancel. And so the overall reaction is going to look like this. The overall reaction is going to be 2 nitrates plus 8H plus 3 coppers, solids. This is going to produce 2 NO gas plus 4 H2O, liquids, plus 3 copper 2 plus. This is the most likely reaction to occur because what I did was I picked the strongest oxidizer and reacted with the strongest reducer present. But it doesn't necessarily mean a reaction will occur. You know, it might not be strong enough. To determine if a reaction will occur, we have to look at the driving force. Now, the driving force for this is going from strong, strong to weak, weak. That's what we want. Stronger oxidizer, stronger reducer to weaker oxidizer, weaker reducer. That's what we want for driving force. Now, the way we're going to do that is we're going to do it based on the half reactions here because it's a lot easier to see from the half reactions. And so when I look at the half reactions here, nitrate and H+, that's my oxidizer that's taking electrons here. Copper is my reducer because that's losing electrons here. Okay. Now what I have to do is I have to figure out the downhill direction. So what I need to do is I need to reverse these and see. If I reverse this, then NO and H2O will be my reducer because NO and H2O going backwards will produce electrons. And then copper 2 here going backwards is taking electrons. So this is my oxidizing agent in the reverse direction. And so when I'm looking for driving force, I compare the 2 oxidizing agents, nitrate and H+ versus copper 2+. That's my other oxidizing agent. And then I compare the reducing agents. Copper is my reducing agent going forward, going backwards. My reducing agent is NO and H2O. And so let's see which one's stronger oxidizer. So nitrate and H+ versus copper 2+. Well, nitrate and H+, we start off with that and we end up with copper 2+. This is downhill. This is driving force. So this is going from stronger to weaker. Now we have to go upside down for this. Now we're comparing copper metal with NO and H2O. Well, lithium's at the top. Now we're inverted. This is downhill also. This is driving force here. Copper is a stronger reducing agent than NO and H2O. Which is weaker. And so we have driving force present. And so earlier we had predicted that copper and nitric acid wouldn't react, but they do react. And I don't think you want to memorize this pattern because it starts getting complex. I think it's easier just to do it off the chart method here. Let me see. So let's take a look at some chart problems next. Okay, the chart is here on Piazza. This is the chart here. This is the Chem 1A chart. This is the correct Chem 1A chart. I don't know what happened. In the old edition, they had it right. In the newest edition, they made an accident. Somebody made an accident and put copper 1 instead of copper 2. But this chart has copper 2. This is from the old Chem 1A book. The acids we'll talk about next time. Well, maybe today. We'll see. So that's the charts here on Piazza. Look at some practice problems. This is for Chem 1B, but some of these are appropriate for Chem 4. All right, so I'd like you to look at which ones are chart. Okay, do this one, number 5, chart method. Chart method, 4, 5, 9, 10, 11, 12, 13, 14, 15. These are all chart method. And so why don't you start off with number 4 and then give these a shot. I'm gonna break you guys up into rooms so you can work together on these. And, I don't know how far we'll get. We'll just go for a little bit and see how it goes. How do you get H2O? The H2O from the H plus, you just see it in the chart. Whatever forms H2O is gonna, one of the patterns is whatever forms H2O has H plus added. And so H plus is critical for formation of H2O. The H2O, I don't get it. I just see it. You know, when you look at the chart, you see H2O. Then you figure it out there. We'll look at H2O some more. I'll have something else to say about it as well. All right, why don't you just try using the chart method, or at least get started trying to use the chart method. We're going to do breakout rooms here. So let's see, if you have a preference in your room, let me know, and I'll set up a room for it. Let me see here. I'm going to have 4 people per room, so try to do this. So if you have a preference, let me know.
No.
I can rearrange the rooms if you'd like as well. Just let me know. I can, if you'd like to join up with your friend. Otherwise, I just kind of did a random pattern. So try these. These are all chart method type problems. Try these and see what you get. The first one, number 4, is very similar. We already did that, except it was potassium iodide. So you could skip number 4 if you want, or you could do it, you know. We did it using the pattern, you know, the single replacement halogen pattern, but here you could do it using the chart method. And so I recommend doing number 4 as the chart method here. So again, we did it using a different method when we did chlorine with potassium iodide. Okay. All right, work on these and then let me know if you have any questions. It's actually, let's see, it's almost break time. It was another 11 minutes. So work on this for 11 minutes and then you can take a break and we'll come back and we're going to continue working on this. Okay. And then the thing about the chart is you just got to get started, and then you don't have to know a lot of chemistry. You know, you don't have to do the oxidation states. You don't have to know the reactivities or this kind of stuff. You just have to be able to find the species on the chart and write down the equations. And so, take a look at that. I'll check in with you guys. If you need help, let me know though.